and welcome to this video where we are going to learn about linear dependence and linear independence of solutions to differential equation, and we are also going to see the Wronskian test and what it is all about. So strap in and let's get to work. Now let's understand what it is meant by linear dependence and linear independence of solutions of a differential equation. So assume there are n solutions from an nth order homogeneous linear ordinary differential equation, okay, given by, so I'm particular now on their solutions. So the solutions is given to me as y1, y2, y3, and so on, and yn. Okay, so assuming that there are n solutions from an nth order homogeneous linear differential equation given to me by y1, y2, y3 up to yn. So we want to make some assumptions concerning the nature of these solutions. Okay, assuming also that these solutions are continuous and defined in some interval denoted by a, b, okay, where a is less than b. Okay, so this second assumption is trying to tell us that we have gotten the solutions of the nth order homogeneous linear differential equations, and we are also assuming that these solutions are continuous and defined in a particular interval. Let me say an abstract interval or an arbitrary interval a, b, and a is said to be less than b. So we will now say that these solutions are linearly dependent in this interval. Therefore, these solutions, okay, y1, y2, y3, and so on, yn, are said to be linearly dependent in the interval a, b. Okay, if, take note of this, the condition for these solutions to be linearly independent in this interval a, b is if there are constants k1, k2, k3, kn. Okay, so there are n constants, not all zero, such that when we carry out some multiplications of the solution and superposition theory in this way, k1 times y1 plus k2 times y2 plus k3 times y3 plus plus kn times yn. So if we multiply these constants by the respective solutions and if we add them, then their results should be equal to 0 if they are linearly independent. So the condition for linear independence is that if there exist constants k1, k2, k3 and not all of them are equal to 0, at least one of these constants should be non-zero, so that when you multiply these constants by the solutions and when you add them up, okay, then you're going to get 0. So if there are constants like this and the solutions of the nth order homogeneous differential equation satisfy this condition, then we say that these solutions are linearly independent in the interval. Okay, so it is important that when you're stating the definition of linear dependence, you should stress on the importance of that interval, because you don't know what could happen somewhere outside of the interval. It could be that the solutions could be linearly independent in this interval, then in another interval it could be linearly dependent, you understand, and vice versa. So the behavior of the solutions may not be consistent over the whole real number line. So it is very important that we need to specify an interval, okay, per time when we want to take our test. We need to be sure that we are carrying it out under an interval, and the interval is going to be an interval such that the solutions are continuous, okay, and they are defined. And this not just the solutions and their derivatives, they are also continuous and they are defined in this particular interval. Okay, so if you have your solutions of your differential equation in this particular interval being continuous and what defined in the interval, and if there are some constants to not all zero, such that when you multiply the constants accordingly with your solution and it all adds up to zero, then you can conclude that your solutions are linearly dependent. Okay, your solutions are linearly dependent. So otherwise, if this particular sum is not equal to zero, if the summation of k times y, ki times yi, so let's say I starts with 1 and I tends to n. So if the summation is not equal to 0, okay, then the solution set, okay, y1, y2, y3 and so on, yn is linearly independent. Is that okay? So this is the definition of linear dependence and linear independence. So another way of seeing linear dependence is that, for instance, the solutions are such that if you check one or two of the solution sets, you'll discover that maybe y2 is actually gotten by multiplying y1 by something, or y3 is gotten by maybe some linear combination of maybe all other functions in this particular solution set. So linear independence is just trying to tell me that one of the solutions in the solution set is actually a constant multiple of another solution, and so on and so forth. So linear independence is a scenario where each solutions are actually unique. You cannot get one solution by multiplying a constant with another solution, or you cannot carry out some linear combinations in the solution set to get one of the solutions in the set. So each solutions are actually unique. They are actually separate on their own terms. They kind of like exist on their own and not gotten by some kind of multiplication or addition or superposition of other solutions. They just exist on their own. So that's linearly independent solution. But linear dependence, constant multiple of one solution gives you another solution in the solution set. You understand that scenario? So like that. So along the line, when you begin to deal with many of these solutions, like when you begin to deal with nth order differential equations where n is a large number, for instance, so you may get to where you're carrying out this particular test to look for this particular constants, you understand, to look for these constants and to perhaps verify this hypothesis over here. So that is why we have to resort to another method of actually checking whether the solutions are linearly dependent or linearly independent, and this will now introduce us to the Wronskian test. So the Wronskian test is majorly used to verify whether some solutions from an nth order homogeneous linear differential equations are actually linearly dependent or linearly independent. So this is how we can actually carry out the Wronskian test. So Wronskian Wronskian. You have to get used to pronouncing this word. Okay, so test. So the Wronskian of some solutions set, that is y1, y2, y3, y4, and so on, yn. Okay, the Wronskian of this solution set. Okay, assuming y is a function of t, for instance, is an n by n determinant, n by n determinant matrix whose value determines whether the solution set is linearly dependent or not. So if the Wronskian is 0, if the Wronskian equal to 0, the solution set is linearly dependent. Is that okay? So if the Wronskian is not 0, then the solution set is linearly independent. Is that okay? So if the Wronskian is 0, the solution set is linearly independent. If the Wronskian is not 0, the solution set is linearly independent. Is that okay? So the Wronskian of the solution set y1, y2, y3, yn is given as follows. So if you want to find the Wronskian, what you can use to determine it is w of, we have y1, y2, y3, and so on, and you have your yn, and assuming all of them are functions of t or maybe of x, depending on what your independent variable is. So you're now going to find a determinant. So the determinant matrix is going to be in this way. Okay, so the first row is the base forms of your solution. So you have y1, y2, y3, y4, dots, we have yn. Is that okay? So the next row is going to be our y1 prime. Okay, so y2 prime, y3 prime, y4 prime, yn prime. So the next row is going to be our y1 prime second derivative, y2 prime, okay, y3 prime, y4 prime, and so on, yn prime. So we are going to take y1 prime, okay, y2 prime, y3 prime, y4 prime, yn prime. So we'll keep going till we now get finally to our y1 to the n minus 1 derivative, the n minus 1 derivative. So you also have your y2 to the n minus 1 derivative, your y3 to the n minus 1 derivative, and your y4 to the n minus 1 derivative, and so on and so forth. Then we'll now finally end at yn to the n minus 1th derivative. Is that okay? So this is how we generate the Wronskian determinant matrix. After generating this matrix, you evaluate the determinants, and just like we said, when the determinant is not 0, so the determinant is not 0, we have linearly independence. So if the Wronskian is 0, we have linearly independent solutions. Okay, so this is how we evaluate linear dependence and linear independence through the Wronskian test. So in the next video, we're going to dive into examples, okay, solving for whether some solutions are linearly dependent or linearly independent, and we're going to be doing that majorly through the Wronskian test. So remember all what we've learned so far, the definition, the theories, the hypotheses, the lemmas, all of them. Just remember them, and I hope you'll be able to reproduce them perhaps in an exam scenario when you're writing a test. So these are the conditions for linear dependence and linear independence. So thank you for watching. I believe you understand these things more clearly when we use examples to expose details about them. So watch out for the next video on the playlist. See you. So then, don't forget to like, subscribe, share, hit the notification button so that you can be updated on more videos. So bye.